If you've ever studied anything at all to do with computer networking, you'll almost certainly have heard of the OSI model. For over 40 years, this model has been decorating the early chapters of networking textbooks as a description of how networking is implemented as a stack of 7 layers, starting from the physical media layer at the bottom, which covers everything from cables and radios to pigeons. As you move up the stack, the layers become increasingly abstract, culminating in the application layer at the top. This is where humans typically interact with the network through web browsers, instant messengers, and so forth. But what's rarely even acknowledged nowadays is that OSI is far more than this 7-layer model, and it was in fact a fully fleshed out set of standards and networking protocols that were originally intended to be the underlying technology of the internet before TCP/IP usurped it. It all goes back to the 60s, when people were starting to try and find ways to get their computers to talk to each other. The US Department of Defense established a research team in an attempt to develop a standard way for computers to communicate that was decentralized and not dependent on specific manufacturers. This was the ARPANET. Over a decade, it brought forth a whole suite of concepts and protocols, including TCP/IP, which proved very effective, robust, and scalable. By the late 1970s, other countries had started to standardise their national computing infrastructures using their own protocols and technology, and so it became apparent that an international standard was needed so that we could all join hands across the globe in perfect harmony. So, in 1978, the International Organization for Standards, ISO, yeah, I know, started working on an open standard for international computer networks, which they named, confusingly, OSI. The 7-layer model was born. The revolutionary idea of the layers allowed a modular approach to networking, so that each layer only needed to know how to pass messages to the adjacent layers and could remain ignorant about the rest of the stack. Sending a message from one system to the other would involve it moving down through the stack until it reaches the physical layer, at which point it's transmitted. At the other end, the physical layer would receive the message and pass it up through the stack to the correct recipient. Conceptually, each layer would believe it was directly communicating with its counterpart layer in the other system. You may be wondering why there are 7 layers in particular, and that's a really good question. Obviously, the ISO thought it provided the optimal set of separations and abstractions, but I can't help thinking there's just something mystical around the number 7, or maybe it was someone on the committee's lucky number. Who knows? But the ISO didn't stop at the model. They continued to develop protocols and standards for all 7 layers. Not only that, they developed application layer protocols for email, file transfer, and also directory services and a whole bunch of stuff. They were standards producing fools. The UK government was impressed and published the Government Open Systems Interconnection Profile, more commonly known as GOSSIP, which was a specification for implementing OSI as the mandated standard for the UK. Soon afterwards, the US published FIPS 1461, also known as US GOSSIP, which was also a mandate to use OSI. And it wasn't long until the rest of the world followed suit. OSI was the future for global networking, one stack to rule them all. But as we now know, it didn't happen. TCP/IP became the single stack that formed the internet, and OSI all but disappeared. TCP/IP does have a layered protocol stack, but instead of the mystical 7 layers, there are only 4 or 5. The lack of 3 layers doesn't seem to have hampered its effectiveness. So what went wrong? Perhaps the main reason for OSI's failure was the timing. While ISO were busy in their committees over-engineering the minutiae of every single aspect of the mystical 7 layers, the ARPANET was already up and running, with TCP/IP happily allowing computer networks across the world to talk to each other. The various GOSSIP directives meant that this could only be a temporary state of affairs until everyone transitioned to OSI. If you look back at the network documentation from the time, you'll see that people were discussing the OSI transition as a fait accompli, despite the reality of TCP/IP's dominance. This made a lot of sense when you consider the amount of money and effort that had already gone into OSI development by governments and manufacturers alike. For example, the Digital Equipment Corporation, DEC, had re-architected the new version of DECnet networking stack to use OSI at its heart, while the other big hitters like Sun and even Windows had OSI support options. There were numerous other issues with OSI that hindered its adoption, not least of which was the design process. OSI was designed by committee. Meanwhile, TCP/IP was being designed by engineers who were actually using it to collaborate. They dealt with real-world issues that were hindering them and incorporated the solutions into the next revision of the standards proposal. And they were proposals rather than fully fledged standards. Frequently, the actual standards never appeared, and the previous proposals effectively formed the standard. It was a living set of protocols and still is to this day. The over-engineering I alluded to earlier was also a real problem with OSI. The standards were huge and complicated. Even the basic lower levels were orders of magnitude more complex than their TCP/IP equivalent. Whereas TCP/IP had a single network layer, Internet Protocol, OSI had several options, including the Connectionless Network Protocol and the X25 Packet Layer Protocol, PLP. At the transport layer, they both had the option of connection-oriented protocols. OSI had the imaginatively named Transport Protocol, which itself had 5 separate classes of variant, named TP0 to TP4, providing varying levels of error correction and features. Whereas TCP/IP has TCP, which most closely resembles TP4. Another significant area of complexity was addressing. As you may know, the internet uses fixed length addresses, 4 bytes originally and 16 bytes for the new IPv6. The workhorses of the internet, responsible for sending packets of data from one place to another, are called routers, or routers depending on where you're from. And they rely on these addresses for getting the packets to the right place. Routers need to be fast and efficient, so the simpler the addresses, the easier they are to process, and thus the faster the routers can do their job. OSI addresses were known as Network Service Access Points, or NSAPs. Rather than being a fixed length, they could be anywhere from 8 to 20 bytes, depending on the type of communication you wanted. This makes processing of the packets a great deal harder and more resistant to simple hardware optimization. This not only slows down processing, especially considering how comparatively slow the router hardware was at the time, but it also requires more memory and creates more room for bugs. On top of these complexities, getting hold of the standards documents was far more expensive and cumbersome than with TCP/IP, which could just be freely downloaded. OSI consisted of dozens of formal ISO standards, which, apart from anything else, weren't cheap to buy. For some small organisations and businesses, this made implementing the OSI stack far more difficult. Implementing TCP/IP, on the other hand, was free, simpler, and already running across the globe. Despite the failure of OSI to become the single standard for global networking, parts of it still exist and are widely used in 2026, with very few users having any idea of their history. Here are a few examples of the ghosts of OSI that we still see today. Every time you connect to a website, your computer establishes a secure connection. As part of this exchange, the web server presents your computer with a digital certificate containing the various details about the site and prove that it is who it says it is. Here's an extract from the certificate of google.com. These digital certificates are called X509 certificates, and if you've ever set up your own domain name with HTTPS, you'll have needed to obtain one for your own server. X509 refers to an ISO standard that was part of the OSI protocol, named X500. X500 was a vast, complex set of standards that together defined a hierarchical directory system, which was intended to create a global directory of everything and everyone on the network. Your identity within X500 would consist of a hierarchical list of strings going from country down to name. For example, C equals US, O equals Microsoft, OU equals C-Suite, CN equals Bill Gates. If you look back at the Google X509 extract above, you'll notice that it contains the declaration C equals US, O equals Google Trust Services, CN equals WR2, which represents the X500 identity of the issuer of the certificate. A part of OSI which thankfully never took off is X400, which was another technology leviathan that implemented email. It used X500 addressing so that your email address could have been something like C equals US, O equals Example University, OU equals English Department, CN equals Arnold Student, rather than a.student@example.edu. The core of X500 itself lives on, albeit in a very cut down form. called the Lightweight Directory Access Protocol, LDAP for short. LDAP kept the same principles as X500 but in a far simpler and easier to implement way. As LDAP began to take off in various organisations, Microsoft took it and mutated it into what became Active Directory, which in turn became the de facto standard for corporate network management. As well as X509 surviving, one of its component standards is still widely used today, especially in telecommunications protocols. ASN1, aka Abstract Syntax Notation 1. ASN1 defines a binary format for efficiently representing complex data structure. X509 certificates use ASN1 for encoding all of their fields and data. Whenever you make a call over 5G, ASN1 is used by the telecoms networks as part of the protocol. And there are numerous other living fossils from OSI in use today. Yet OSI itself is almost unknown. I can't personally say I'm sorry that OSI became extinct. I once had to try and diagnose some issues with an OSI implementation, and it was painful. Give me TCP/IP any day. As a final thought, it's quite ironic that the 7-layer of the OSI model is still used when teaching networking, yet what's not taught is what happened when it was actually implemented.